you basically following me more correctly. So what's well logging? Operation, basic petrophysics, different type of measurements. So this is the outline of this. We should be able to finish around 11. I think 11, just before, a little bit before 11, because there is a tea break, and then 11:10 the next session starts. So we don't want to delay the following session. So I think we have a reasonable number now. Some people are just rushing in to come. So good to see all this number. Let's move on this with the different topics. So first one is what is well logging? So log is basically, it's a record of uh, the sensor measuring downhole with the depth reference at regular intervals. So that basically called a log. And what we do in that, we load sensors into the well bore to measure the rock properties. So most of you might be geoscientists, some engineers. So I believe some basic concept you already have. So why do we log? So all these reasons you can read. Finding hydrocarbons, hydrocarbon type mean gas, oil, how much volume, what type of fluid will flow and what rate. Oil companies drill these exploration development wells. That's their main objective. And then based on the different measurements, the data we get downhole, which come to the surface, being processed, analyzed by different experts to optimize well construction, mean how the well basically will be drilled, completed. Also the same data can be utilized for the next wells. So two major ways of logging while drilling. So as the well is being drilled, the same time the data is being acquired, called logging while drilling, LWD. And the measurement of formation properties during drilling or shortly thereafter. I mean, the bit is head of everything, and bit drilled something and sensors above in the drilling assembly. So bit just penetrates and then we measure the data. So that's basically, it's while drilling or just a little bit after. So this, it means the tools and sensors are attached to the drilling assembly. So as it's drilled, as being the data is acquired. It could be vertical wells or it could be horizontal wells. How we get the downhole, the rock properties through the measurements we're converting into electrical sort of pulses or some sort of inferences which need to be transmit uphole. So in case of drilling, logging while drilling, we use basically mud which sends the signal up, because it has a drilling borehole fluid which is called drilling mud. The second is wireline. Wireline means that the well is drilled to certain depth, and then it reach to the certain section TD or final well TD, and then we load the different tools, different sensors attached to that, and that we called, because it's attached with a certain wire, a cable, so that's why we called wireline. So you see on the right hand side some sort of equipment. More important is this winch, where this cable is spooled, and next you will see it run through the So run through the different wheels and then go into the downhole. So on the left hand side, you can see that with the how the technology evolves, everything else, same with us, logging, that we have very basic equipment in the beginning, and then more modern on the right hand side. So this data is presented in different graphical format with a different type of measurements. So this was just quick few introduction, what the well logging, why we log, what types, and then we look at the operations at the well site. So well site has this, could be land or offshore, had different unit we call a truck, you can call, which we drive to the well site, or if it's offshore, then we land it on we put it on a platform. It has different, of course, setup, and for engineers to work through, and with the operator, technician with him, to set up the tools and then load into the borehole. So we'll go through in that. So if you, this is the red arrow, you can see that it is the cable leaving the unit, go through certain, we call wheels, sheaves, and then up to the mast, and then goes to the bottom of the hole. So I earlier mentioned about wireline cable. So this wireline cable is has multiple layers. We called multi-conductor, and some sort of sleeves, rubber, to protect that cable. Some inner layer, outer layer, but inside it has a conductor which can transmit the data uphole. And it is multiple cables for different purposes. So the one, the bottom one called lower sheave wheel. This sheave wheel is at the rig floor. So it is in sort of high tension, and should be avoided to get close to that. You know, in this well site operations, you need to be do everything with very safe, with certain precautions. So this is the upper one, the upper sheave wheel, from where these cable spools and come down. On the right hand side, you see this is like a pipe, metal rod, has different sensors, and some like arm type assembly which can open, maybe calipers. Caliper is which the device read the borehole diameter, radius or diameter. So this is overview of common tools. On your left, you see we have different measurements to do a formation evaluation, describe a rock properties. We have to collect different type of measurements. We cannot get everything just one go. Sometimes we do multiple runs. Runs mean you load the tool into the borehole, get some data continuously over the depth, then come on the surface, make up another tool string, run it again. So this is called run. So sometimes you have to run multiple runs. So on the left hand side, you see resistivity, density, porosity. This we called basic logs. Next, sonic with caliper. Caliper the one has multiple arms because we need to read the borehole diameter. Formation tester. We're not talking everyone in the rest of the course, but some more. So formation tester is more on reservoir pressures, reservoir sampling. Last one, imaging. Images is the resistivity imaging around the borehole, 360 degree. So formation tester more for engineers, reservoir engineer, petroleum engineers. Imaging more on geologists, because if you work on the core data, and this we call electrical coring. It means whatever you see, the layering information, any geological stratification you can get via this imaging tool. So rig up. So rig up is the term used that when the logging operation is about to start, the field engineer prepare tools. So basically, the tool is in different parts, you assemble together, and then you check on the functioning at the well site before lowering into borehole horizontally. Horizontally mean they are lying in parallel to the surface, and then you bring to the vertical to the rig floor, and then you test again. The current is flowing, the arm is working, the basic, and also you do some certain calibrations. So certain checks before lowering the tool, yeah. So in logging operation, as you see that, we have some real-time data transmission from the well site to the customer offices, as well as to our office, where different experts are looking at the data real time and advising the field operations to adjust certain parameters, to do certain corrections. So basically, data is being acquired, uploaded real time through basically satellite connections, then finalized and processed by at the well site. Engineer has certain processing, and in the offices, us from the service company and from the oil and gas company, certain people also experts on these data handling, they also look at the data and do certain analysis. And then they basically generate final product, which is being shown to the management or a team, as a team, the working for that well field to do certain decisions, way forward plans. So this, you can see that this is how the tool is being lowered. So how we present the data in graphical, we called field print or log, field log. So field log has certain curves displayed, different colors, different scales, quite standard. So the doctor look at the X-ray and he knows what this wiggles means. Similarly, log analysts, whether they are petrophysicists or geologists or reservoir engineers, they also get expert on reading these logs, and they know what color it could be, what scale it could be. So that's why it was standardized. So we don't need to look at every time. We look at the response, and then you can hear me, and then we can also see what these logs shows. So now we look at this, the interesting part of this basic petrophysics. So as I mentioned earlier, that some part is very, very basic. You might see, oh, we know it already. You need to bear with this. Some may say, oh, I have not seen it. So, in the mixed course, there is always basic, middle, advanced things. So petrophysics is the study of physical and chemical rock properties and their interaction with fluids. Very basic things, yeah. So rocks, fluids, their interaction. That's what we need to know that. So petro is like a rock. We want to answer important questions. What is the value of hydrocarbon in place? And to answer that, we need to know thickness, porosity, saturation, area, hydrocarbon type I mean gas and oil. How easily can the hydrocarbon flow? But it means the permeability and pressure. Pressure is the energy which basically forces the fluid to come out of the rock, flow into the borehole and come to the surface. So that's reservoir pressure is very important. How easy it is to drill to the reservoir? That depends on lithology, what rock types we are dealing with, depth, pressure, pore pressure, temperature, bottom hole temperature, formation temperature. So we look at these things one by one. So porosity. Porosity is a wide space between grains that can contain hydrocarbons. So ratio of the pore volume to the rock volume. It's expressed in percentage units. We quite oftenly called PU, percentage units. How much porosity? 5 PU, mean percent. So you can see that on left hand side, there is a more wide space between grains, whereas in less space in right hand side figure. So it means the wide space where we are interested in in terms of porosity is varies as the grain size and the grains are packed or sorted. So the porosity depends on all this. We can see also these sections and under microscope, the petrographic section, and we can also find out different mineralogies and the pore space. The next one is permeability. So permeability, as we already seen, this is the ease with which the fluid can move out of the rock to the borehole and then to the surface, and this basically a path along which the fluid moves. If path is straight, easy, we say high permeability. If it's more smaller, zigzag, tortuous, then the permeability will be low and fluid has difficulty to move. So the permeability is also very important. Pore space and then permeability. So measure of the ease with which fluids can flow through the rock, often closely related to porosity. Sometime not. In terms of fractures reservoir, the porosity will be very low, but permeability very high. But otherwise, the porosity and permeability have good relationship. Yeah, yes, yeah. Okay. The the range, yeah, porosity ranges are highly variable, as low as 0, as high as the rock can withstand with that porosity. You know, we don't want the rock need to be solid and has consolidated. So in that terms, maybe 30 to 40 PUs could be highest. I mean ranges wise, okay, range wise, in Middle East is high porosity carbonates, like average 20-25. In Pakistan we have not that high porosity reservoirs. Here we have, if 10 to 15 we consider good enough. Permeability is expressed in millidarcies. It's good in that we have in a double digit millidarcy. Then it's Darcy is excellent, but double digit millidarcy probably considered a good workable range. When we say tight rock, unconventional rock, then permeability ranges are in decimals, or for shales even in micro and nano millidarcies. So this you can see this drilling mud fluid packing it could be in the case of borehole as well, but in the rock as flushing into the rock as well, it can create some problems, and particularly the permeability. So what is the water saturation? We talk a little bit porosity, permeability, and no saturation, and we quite oftenly call water saturation. This is just the convention. Normally our main goal is the hydrocarbon saturation, but you know, our equations are made such that we compute water saturation, and 1 minus SW is amount of hydrocarbon. Amount of hydrocarbon could be gas and oil. That's another split further required based on the extra measurement. But when we say what is the saturation, the commonly we talk about water saturation. And when I say water saturation is very low, is automatically assume hydrocarbon saturation is high, and vice versa. So you can see that here, this in the water blue, rock yellow, hydrocarbon black, and in the structural trap or some sort of trap, you can see that water below and oil above, hydrocarbon above. So basically the water saturation is the fraction of porosity that contains water. Basically at the end it's the porosity, the storage capacity, which will be filled by something. So the initial goal to find a porosity, and then find out it can contain all water, it can contain most of hydrocarbon, or it can be in between with any percentage. Yeah. So what is the water saturation, the fraction of porosity that contains water? If you look at the top figure on left hand side, SW is quite, blue is very low, blue portion is very low, so we call it water portion is very small. In the middle is mix, some black, some blue, and the bottom one is all blue. So it means the bottom one is not our target from oil and gas point of view. So we will be quite happy to have the top one, but the middle one we can also work with to produce that hydrocarbon as well. What equation can be used to find SW? So very famous, Gus Archie coined this equation in 1940s, and still being used with advanced measurement. Although different modified forms of this equation exist available, but the basic equation is still quite oftenly used. So this equation is a relationship between the rock properties in terms of rock resistivity, fluid resistivity, and then saturations. And of course there is a certain constant A, which is a empirical constant, mostly close to 1. If we don't have any raw data, mostly from core information, then we assume A is equal to 1. The other one is M, cementation exponent, we consider normally is 2. It can vary, but that's what I'm saying, we assume if we don't have external information. And saturation exponent, we also assume 2 if we don't have external information. So this equation can be written in different form. We can bring the RT on this side and SW on the other side. We can bring RW on this side. But important measurements to remember is saturation, resistivity of water, RW, the fluid, how much saline, less saline, more or less saline, RT, resistivity of true resistivity, formation resistivity. This we measure. This is a measurement. This is a type of log we do. Phi. This is a symbol used for porosity. When we say phi, it is a porosity. RW determination using RT equation. So when we're doing log interpretation, our major input in log interpretation is that we measure the porosity, we measure the resistivity, but we need to know that when we convert this porosity is occupied by a certain fluid. So resistivity log profile, high or low, will use to drive the saturation. An important parameter to use that is the water resistivity. The water resistivity can push the resistivity up or down, and the rest is going to be hydrocarbon. So the RW is, any person working on the logs, a petrophysicist, geologist, has to go through this RW, and based on this known information, produce water salinities or nearby areas, this parameter we can calculate. Otherwise, if we have log data and certain formation is confirmed it's containing water because low resistivity, high porosity, so we think this could be water bearing, in between medium resistivity, transition, high resistivity hydrocarbon. So if I have a water bearing zone, then we don't need external information. We can calculate it from that particular log data. So it means we assume that water rock is 100% water bearing, then SW becomes 1, and then A1, M2, N2. So if you put all this equation simplifies into RW is equal to phi square RT. So if you have you know the porosity, you know the log resistivity, you multiply that, so this RW will be valid for that particular data in water bearing zone, because we assume SW1. So if we have permeability, what will happen in the formation? So if you see that uh, overlaying shale rock, some reservoir rock which has porosity, permeability, and then different fluid, gas, oil, water. So as the drilling mud, the bit drills, there is a mud in the borehole which will go into the borehole and will make this concentration along the borehole, the wall, and some may fines penetrate to the formation. So we called this is mud cake. Mud cake means the fines will deposit along the borehole and the liquid part penetrate into the formation. We call it invasion. So it means you will have a borehole and then some flushed zone and then uninnervated zone or virgin zone. So it means if rock is very permeable, there will be lot of invasion, lot of borehole fluid going into the formation, because drilling mud will be over pressure, higher pressure than the formant fluid. So not only it keeping the formation fluid inside, but also pushing the borehole fluid inside. That's called overbalanced drilling. So this is very famous diagram we show. The drilling process complicates our measurements. The formation away from the borehole is divided into 3 zones. We call it flushed, transition, and virgin. So which is fully the dark blue, which is basically flush the borehole fluid, mud or water, flush the hydrocarbon away. So that's first part. Second is transition, mean partially. It means some mud, some hydrocarbon. The last one, it means the drilling mud has not gone into that deep enough. So it means it's still keeping the borehole fluid, formation fluids untouched. So flushed, transition, and unadvated zone. So an unadvated zone resistivity saturation equation has different mnemonics than unadvated. Instead of SW we called SXO. Instead of RW we called RMF, resistivity of mud filtrate. And instead of resistivity RT we called RXO, shallow resistivity, instead of deep resistivity. So basic log data and how to read a log. So on your right hand side we see 1, 2, 3 different, we call tracks, different tracks displaying different curves with different texture and color. So reservoir properties, reservoir zones, is the shale versus sand. We look at the gamma ray tool on a first track, green color. Although we say shale sand, but in more reality we say gamma ray is a radioactivity, formation radioactivity, natural radioactivity. It means some formation are more radioactive, some formation are less radioactive. More formation radioactive could be shale, could be else, but for simple reason we say shale. And clean, low gamma ray, we call it clean formation, and clean formation could be sand, could be carbonate, could be anything else. So the gamma ray is not only because shale sand, it could be else. Some radioactive minerals also complicate lithology. So that's why we more call radioactive formation high gamma ray or low gamma ray, rather than calling shale sand. The next is the porosity, which is the number 2 track. Now we will display density and neutron logs, help us to find porosity along with sonic as well. And then in the middle we have resistivity, which tells us the fluid types. So gamma ray, low shave volume in reservoirs. The blue line is porosity lines, low or high, whatever. We're showing that with decreasing trend towards the depth. And resistivity, this red, so you start with high, in the middle is transition, and then at the bottom low. So maybe we can say that the low gamma ray is some reservoir, it has some porosity and hydrocarbon transition and water bearing. So basic petrophysics, and now we look at the different type of measurements. So what we're going to cover in this course is nuclear, resistivity, and acoustic. Under nuclear, we look at gamma ray, density, neutron, spectroscopy, standard basic measurements. Spectroscopy is in the medium category. Sometime we run, sometime we don't run. Acoustic, resistivity. So we look at this one by one. Nuclear first. Starting with gamma ray. So gamma ray is the natural radioactivity. So we have certain sensor, like at surface gamma ray is also measured by giga counters, different type of devices. We also have certain device which measure the natural radioactivity. So you can see that there are different radioactive elements which basically cause the radioactivity: uranium, thorium, potassium, and they are present in mostly common minerals. So we can also split total gamma ray into these three. So we can find out which is uranium rich, which is thorium rich, which is potassium rich. As a geoscientist, we have some knowledge that certain rocks are potassium rich, like feldspars and micas. Some clays are potassium rich, some are less potassium. We can identify different clay types. So this further split gamma ray into all these elements also helps for further knowing the lithology. So basic lithology indicator between low and high, as I mentioned earlier, it used for correlation, from well to well correlation, depth matching. When we have different runs, different measurements, the gamma rays will be in each run. Every log will have a gamma ray, and that used for depth correlation. How we do this depth correlation? Because when we load the tool, there could be some off depth between different runs. So we look at certain peaks and troughs and then try to correlate and bring them on depth. So that's why a gamma ray is being run with each run, each log. So this is basically, we make the first run as a reference and the following runs we shift accordingly. We call depth matching. So these advanced detector also measure the energy of gamma ray spectrum, indicate this thorium, potassium, uranium. This is what I mentioned earlier. So this is the example. On left hand side, you see the gamma ray green color has low and highs in the middle, and on the right hand side, it's more highly variable, highs and lows, which deflect certain mineralogy, different lithology. But it's not as easy to jump straight into saying carbonate and sands, because we need other measurements. But for a simplest reason is mentioned here, but not all high gamma rays are clays, and not all low will be one type of lithology. Now the next one is density. Very important measurement. It's used in different applications. For log evaluation, formation evaluation, for GNG, for geomechanics, any elastic properties. It is quite very important, and it need to be very accurate as well. So the basic formation parameter, each cube have the same value, volume, like 1 cubic meter, but you can see that on weighting device, they shows different weight, because depends how much hollow it is, porous, and then porous part contains what. Okay, so once we measure the density, we know that we call it chart book or a log interpretation book, which has certain tables. The different mineralogy has a certain matrix or grain density. It means if there is no porosity, the sandstone reads 2.65. But as soon as the porosity comes in, it becomes lighter and lighter and lighter. That's what we interested to measure. If you know this is sandstone and it's reading 2.5 instead of 2.65, we fill this in this equation. Porosity is equal to rho matrix this number, minus rho b, the what we log measured, divided by rho matrix minus rho fluid. Rho fluid is the normally water, which is 1. So by this we can find porosity from density alone. So this is how the tool look like. Tool has a radioactive source on one side, and the other side it has one arm which open and touch the borehole wall, which push the density pad to the formation. It must need to touch the formation to make the valid measurement. The nuclear source has it basically emit gamma rays from the source to the formation, which interacts with the formation, and then their response is measured by the different detectors after the interaction. And on the other side is reading the borehole radius diameter, we call caliper mission. Hole is in gauge or hole is enlarged. That's what we also interested. So what type of interaction it go through when the gamma ray leaves the nuclear source from the density tool? They could be in different type of energy, low energy, high energy, and then those different interaction, photoelectric, absorption, and Compton scattering. Of course, I cannot explain too much detail with short of time, but there is a literature available. You can, and also you might have already studied all these nuclear interactions. So this is, you see these green gamma rays passing through the rock and leaving the rock with certain interaction. Some are absorbed, some are captured, reduced, some are slowed down. So what you get different at the detector, what is being left from the source. So some gamma rays are captured. This is a photoelectric absorption effector. And so gamma rays emitted react with the formation, and returning gamma ray made by 3 detectors. In modern density tool, we have 3 different detectors. One close to the source, one in the middle, one is away from the source. So the one away from the source will read deeper into the formation, when close to the source will read close to the borehole and some part of formation. So the combination will give us formation density. By looking at close to the borehole, there is certain effect, and away from the source, deep into the formation, which will be more formation response. So we basically call these density measured by these detectors. There is a software version which is merging all this data into single measurement density, but there are certain associated curves to quality control that density. And those detector density we call backscatter, the closest one, the middle one short spacing, and the far one called long spacing. And you can see with the red color, blue color, and green color that while they are far spaced, they're reading deep into the formation, and that's what we are more interested in too. We want to have the measurement less sensitive to borehole, more sensitive to formation. So this is the counts on y-axis, and the x-axis is their energy, kilo electron volt. So as the new gamma rays leave the tool, they are in high energy. With the time they lose the energy, and then we have this region of their energy spectrums divided into A and B and C. So the low energy in the region A, we measure the information called PEF, photoelectric effect. So this is more indicator of lithology. Like sandstone has different photoelectric effect, limestone carbonates have different, shales have different. The B region, the medium one, more sensitive to the photoelectric absorption, and some part in component scattering as well. But what we interested in density is the component scattering, from where this bulk density is measured. Actually, we read electron density, but it's very much equivalent to the bulk density. So increasing density, fewer gamma rays travel through formation. The formation is very denser, rock is very denser. It captures most of the gamma rays, or only few going to the detectors. As you can see with the bottom blocks, that most of the energy is being absorbed, and then with higher density, the rock is more solid, will be less gamma rays reading to the detector. It means it's more denser or low porosity, high grain density, high matrix. All right. So if you see that the tool how is making the contact with the bore hole on the one side and the caliper measurement on the one side, and it's not just one sort of cylindrical. It's due to certain formation is also getting enlarged as well. We call washout, breakout, enlarged borehole. That's the caliper measurement. So and you see that in case of denser formation, there are only few gamma rays reaching to. There is some question at the end as well, so you might need to watch these slides carefully. So example of this is, as we've seen already, this gamma ray clean, high, green curve. The next one is shown. Normally we display logs in combination, like rather than using one logs as a to know all the information. So here we display density neutron, and their separation or crossovers or overlaying each other has different meanings in terms of lithology and porosity. So this is how we use this density neutron. Visually we can tell someone that this represents this. So this is basically certain color scale, and this is the way we display it. It automatically tells us that bottom one where they separate each other is shale. When they close to each other, water. When they have some separation, the red color is oil. But when they separate too much, gas. But in gas separation is different than shale separation. The green curve is on this side, whereas the bottom on this side, and the gamma is also indicating that it's not clean formation. So this is what I explained already, that the gas being lighter, beside the rock will be lighter due to porosity, but the same porosity is contain gas which is even lighter, the density will be even less. But since gas has less hydrogen index, the neutron will be much lower than as compared to the oil in case. So the porosity in gas and oil might be exactly same, but the logs appearance is different because of one is lighter, one is heavier. So this is grain density of different minerals. The next one is neutron. So we went through the density, and now look at the neutron. So neutron measures the porosity of the rock, also used for gas detection, because in terms of gas it basically shift towards zero, because gas has very low hydrogen index. Neutron reading the hydrogen index. And then we also look at the different together with density lithology information, and it is also nuclear tool. It has a radioactive source. So instead of density where it was bombarding the formation with gamma rays, this neutron tool has neutrons leaving the source. So a different type of source, of course. So the neutron leaves the source, interact with the formation, different type of interactions, and then of course we have detectors, a near detector, two detectors here, and each one will read their response. So neutron leaving the source, reaching the detector maybe in different numbers, and that number means certain information, what we are interested into. With the time, those neutron interacts with the formation and they lose the energy, get slowed down, and those two detector measures their response. So this is a very famous figure we show on this neutron log. Neutron energy on the y-axis, time microseconds in x-axis. So as the neutron source, they are at a certain 10 into 6 electron volt energy. With the time they come out of, they slow down and get at basically very flattish. So early is very high energy. This we called epithermal range. The next level below 0.4 electron volt is called thermal range. And then towards the end, with a different type of collisions, they get captured. And they basically leave the gamma ray out of it. So what we interested in this thermal range to measure this hydrogen index. Hydrogen index is the porosity basically, because the pore is not empty, they contain certain volume, and if you assume if it's all water, it means this is a hydrogen, and that's what we call porosity mean hydrogen index. So in terms of porosity, if we assume a rock, 1 meter cube rock, fast neutrons interact, epithermal range, thermal range. So we, based on the porosity ranges, we get few or more neutrons to the detectors. That determines how much porous is. In case of, we put the tool in water tank, which is 100% porosity, there will be nothing coming to the detectors, which means all captured. So it's all porosity. In case of some porosity, you have higher population on the left-hand side, but less neutron on the right-hand side. So it means rock has some solid part and some porosity. And more important in this is this chlorine, because water is salty, which basically which highly absorber for the neutrons. So how this is how the tool look like. That on one side it has an arm, which we called it bow spring. This is because it's like a bow, but it's a spring. When we run the tool, it is open like this, and what its function is that it pushes the tool body close to the formation borehole wall. It should be touching the borehole wall, because we're not interested in to read borehole, we're interested in to read the formation. So we need to be very close to the formation, borehole face. So if there are a lot of hydrogen atoms, less neutron will return to the detector. With less neutron detector, it is an indication of large porosity. Count rates are inversely proportional to hydrogen. If count rates mean what is reaching to the to the detectors, near and far, we call counts. How many? And it means their counts is basically we will convert into, or they are related to the porosity, which is hydrogen index. That's what figure you already seen it. So Shallier formation has higher neutron porosity. Why higher neutron porosity? Because they have hydroxyl ions. Clays are aluminium hydrosilicates, so they contain a lot of water. So that gives the lot of porosity. Whether this porosity is effective, has some hydrocarbon, or some has permeability. When we talk about a conventional reservoir, we keep away from the shales. But when we talk about the source rock evaluation, unconventional, we are also interested in shales. As you see in US, how much shales are productive, and other countries are also working. Pakistan also has some project on shale gas. So spectroscopy now, next one, in nuclear. Spectroscopy is mainly help you to define different mineralogies. So if you identify information value, your first focus is mineralogy, lithology, porosity, and saturation. This is the sequence. Once you fix your mineralogy, complex mineralogies are always there. Nature is not so simple. Then you need to fix your mineralogy first to have to write with porosity, because If you assume it's a sandstone, actually it's a limestone, you use the wrong grain density to compute porosity. So that's why mineralogy is very important. So it means we need to have some extra measurements, not the density neutron NF. So we can find out matrix density. And with this spectroscopy, we again go to nuclear source tool, which bombard the formation with neutrons and go through different interactions. And here we're starting with the neutron, but we're measuring the gamma rays now. And these, the red color curves, we call spectroscopy spectrums. And those spectrums, you can see these different peaks and troughs. And different minerals have different characteristics on the spectroscopy. Each one will have its own characteristics peak. And through stripping, through analyzing, we can find out how much that mineral, how much that mineral. So towards the end, we put all this together, and we have different spectra, capture spectra, inelastic spectra, because through the interaction, some are captured, some are inelastic, some are elastic as well, but they are very early age. So different interactions we are interested. So you can see that those different colors, different curves, we have colored them differently, has different signatures at different levels based on the energy level and their time. So it means those different minerals are showing different responses. What we need to do that, bring those, because we don't know, we don't have core, maybe cuttings giving up some idea from the bottom, cuttings may be mixed up, depth not accurate. So from the log responses, we want to find out those minerals which we don't know. But geologically, we might have some idea. Formation with stratigraphy, you might have some idea. If you have core, that's best. But coring, you cannot do the whole interval. You do only small intervals. Coring is expensive and time consuming. So it means core information, you can calibrate the logs, but the log is for the whole interval. So the log core information can complement log, but cannot replace it. So basically, with this spectroscopy, we are interested in different elements. Rocks are made by minerals, minerals are made by elements. If we can figure out the elements, we can make the minerals, certain modeling, certain combination, and then go into the rocks. So from rocks to have spectroscopy gave us elements, minerals, rocks. This is how the sequence is. So in nature and surface exposure, you might well site geology, you have seen to different field trips that you have different exposure, different rocks you can identify on the exposures by different their texture, with the acid effect, you can see different mineralogies. And then downhole also we could have all those minerals, quartz, which is sands mainly, and calcite is mainly limestone. So we display on this side gamma ray, resistivity and density neutron. So the question here is, what is the lithology here? So low gamma ray could be limestone, could be sandstone. You mean it's difficult to say unless we look at the other curves. And PEF is around 5 to 6. Each line is 2. And the density neutron overlaying each other. It means they are more likely limestone. This no gamma is high. Resistivity is very low. All the curves are on top of each other. Density neutron separating. Neutron high, density lower side. So what could be the lithology? Any guess? So it's mixed lithology, mostly shaly, some calcite, some quartz. All right. So as we mentioned earlier that with the spectroscopy, we're starting from the yields. Yields mean how much hydrogen, chlorine, barium, silica, calcium, iron, sulfur, titanium, gadolinium we measured. Yeah, yes. Okay, yeah, see, the gamma is low. So gamma is low mean a clean formation. The clean formation can be sandstone or limestone. Resistivity is low or high based on the porosity, but yeah, in the middle, yeah, this curve, in the basically second track from the right. But we are talking about the lithology at the moment, so let's forget the resistivity. Gamma ray tells us clean formation. There is on your last track, the first curve is not visible much, but it's a PEF. PEF is a reading 2, 4, 6, less than 6, maybe 5.5. And then density neutron on top of each other. So when PEF is around 5 plus minus, it's not sand, and it's not shale because gamma ray is low, so more like carbonate. Limestone, dolomite has low PEF, limestone has a high PEF, and density neutron overlaying each other, so that's porosity. But lithology wise, limestone from PEF and gamma ray. Okay, so yields, spectra, those spectra we already seen it in those these curves, and we basically software stripping out of that. That's the tool measures and stripping out of the elements, yields to elements, to minerals and rocks. This we already talked about. Now we look at the resistivity. On resistivity, basically we're interested in knowing the saturation, the fluid type. So resistivity is the basic role. This is Schlumberger did 1927 first log in Paris, in France. The first log was measured resistivity. So this whole logging came out of this. We'll show you the picture as well. So resistivity is basically could be low or high, and that depends on the amount of type of fluid it contains. Water being low resistivity because mostly, not always, but mostly water has salts in it, saline water. Meaning salinity makes the resistivity to read low, conductive. Low resistivity also talk about more conductive. And hydrocarbons, gas or oil are insulator. They don't allow current to pass, so they could be very resistive. The question comes, if water is also low salinity, we call it fresh. If water is also fresh, then it becomes really difficult to identify hydrocarbons from water if water is also fresh. And there are certain cases, so then we have to look at some more other measurements. So this is the RT equation, this RT, the red circle. This is what we aim when we measuring the resistivity measurement to conclude this resistivity of formation. Of course, we will have a different type of tools, different their makeup, and right hand side, left hand side is the induction type of resistivity, and right hand side lateral log resistivity. So this is basically two principally different measurements we do in different environments, different type of muds. Induction is run, and lateral log is run in different environment. In Pakistan, we mostly do lateral log because of our borehole and drilling fluid and formation characteristics. Both of them I will explain. We'll go into one by one. One, induction induced current. Lateral log emits current. So as I mentioned, here it's difficult to before 11 we have to finish. The literature available, which can you go into www.slb.com. You can download or can contact me to get certain literature. But our www.slb.com has a lot of information, background information about these theories. So if you look at this borehole, where we have tools, the induction is the bottom one induces current in the formation, and it's like a parallel circuit. If you have some sort of electronics read as a subject, you might see this, that current goes into parallel or in series. In case of induction, since it induces the current through coils, and then it goes a, a as a parallel circuit, whereas in lateral log, since it's emitting the current, then it's going into different series, which is through like a serial circuit to the formation. And of course, we will have borehole and then formation, and then different electrodes on the tool body. So we go one by one. First, induction. Induction, the tool string like a metal pipe or rod, which has attached different electrodes, measuring devices. Electrode mean measuring devices. Current, you know this current equation. We look at the Ohm's law. You might have heard about it. So in induction, we have multiple arrays with variable spacing. Some making measurement close to the borehole, some deep into the formation. So that's why we have all those A1, 2, 3, 4, 5, 6, all those different electrodes, sending the current to the formation and then receiving the current to the. So through this resistivity, we don't have, instead of getting one single measurement, we get multiple measurements, which have different depth of investigation. There's two terms we quite often use in logs: depth of investigation, how deep we read into formation, and second thing is vertical resolution, how fine we can read between the layers. So if you're reading deep into the formation, your vertical resolution will be less because it's reading deeper. So you need times to reach to the device. But if you want more high vertical resolution like formation imaging, then you need to reading very close to the borehole, because then remaining devices are very close to the electrode and source. So then depth investigation and vertical resolution are reciprocal to each other. So in this in induction, we have different type of vertical resolution. On the top one, you see that smoother to very sharp, and then different depth investigation, reading close to the borehole, 10 inch, 20 inch, 30, 40, 60 inches. 60 inch deep into the formation. If you read as away from the borehole, more will be representative of the formation because of invasion, the penetration of the drilling fluid into the formation. So in induction, I mentioned as earlier that it has different coils, and when we induce current, it creates a magnetic field. We call it primary magnetic field, and that primary magnetic field or flux induce current, and they create another secondary magnetic field that's being measured by our receiver coil. So from transmitter coil to receiver coil, from current to magnetic field to current. So that's the basic principle of the induction measurement. The second, lateral log. So lateral log has a measuring electrode emits current using bucking electrode to force into the formation. Currents sent at different frequencies. So different frequency we use in induction, different frequency we use in lateral log. And here we measure, you can see this series of electrodes on this tool body. In the old tools, we used to send the current to the surface, but in the modern lateral log tool, it is being sent to the tool body. So there's nothing at the surface, and it has different issues and different advantages. So here we're saying we read 6 modes simultaneously. With this blue color, you can see that the current leaving the body, going into the formation, reaching to the receiving electrodes, and having different depth of investigations. So physically, currents are set at different frequencies in 7 working modes, from left to right, the shallow to deep. As you can see, that shallow is very close, more sharper, where deep is more smoother. So we call it mode 0 to mode 7, and each mode will have a resistivity value close to the borehole and away from the borehole, deep into the formation. When we have a drilling fluid water base, which is most of the case, Then we run lateral log. When drilling fluid is OBM, oil-based mud, which is not oftenly used but still used in certain lithologies, shelly formations are not stable to drill. They create problem. They basically caves or they swell. So they basically not easy to drill water-based. So oil and gas companies drill with them oil-based mud. It's very expensive, but this is the drilling challenge they have to tackle. So they use oil. Oil is basically diesel. So in that case, lateral log will not work. Lateral log requires conductive mud because it can emit current. Whereas adduction working as inducing current through magnetic field, so it means it can work in fresh mud. Fresh mud means low salinity mud, which is an oil-based mud. So that's the basic fundamental difference between two. Since we run very oftenly water-based mud, so in Pakistan we run mostly lateral log measurement. Lateral log is type of measurement. The tool name is different. So if you see this on this curve gamma ray and then those resistivity curves, above and below on reading all curves together, looks to you one curve. We say overlaying. But in the middle, low gamma ray, they showing you separation. So shallow one to deep one. What this separation mean? Different things. We have to see, normally we don't jump into one collision looking at the one log. We look at all the logs together and then see what it could be. So on this side we have, so it means we see invasion, probably, separation. And on this side, left hand side, we have all the resistivity curves reading on top of each other. So it means no invasion. Yeah, of course. Yeah, when you are dealing with the oil-based mud, it means oil is penetrating into the formation and flushing the hydrocarbon, flushing the conductive saline water, all resistivity reading same. But in the case of water-based mud, it means you're using saline mud flushing the hydrocarbon, flushing the water, which could be less saline. So it means close to your borehole reading, more salinity, it means more mud, less mud, less mud, less mud. So it means this is your based on the drilling mud type as well. And so that basically, you have to remember, three things: flushed, transition, uninvaded. So based on that, this resistivity profile can vary accordingly. So in resistivity, as we started with the petrophysics introduction, that we interested in pore space, and pore space, what fluid it is, and that's what we're using now. We have gamma ray, we have density neutron, we have resistivity at the end. And so black hydrocarbon, the lower one, most likely water. All right, so resistivity, as you can see that as high as possible has a relationship with the saturation on x-axis. If your hydrocarbon saturation is close to zero, resistivity is very low, you will have mostly water. In case of fresh water, you go resistivity high, still no hydrocarbon, right? But if you have saline water and resistivity high, hydrocarbon saturation medium, you see you get more and more black. So this is how it works. So this is a log example. Gamma ray in the left, resistivity in the middle, and density neutron on the right hand side. So their lows and highs, their deflections, right to towards left has certain meaning. So with the expert eye, you need to able to understand without looking at their scales that what it could be, what it could be, what it could be. Of course, then softwares are available which use this data digitally and give you answer product in terms of, and you also student might have also calculated by manually, by hand, you can also calculate at different depths, which is good check, because software you might have some bug or some error in your input. Better to check few points manually with calculator as well. to that you don't basically send someone or give someone or present some wrong results. So where are the sandstones? We look at the low gamma ray sections. Where is the gas? We look at the density neutron separations. Where is the oil? Of course, we look at the density neutron and the high resistivity for gas and oil both. So we mark this red color, and then we mark green color below. Where is the water? So you could have water in between gas and oil. You could have water at the bottom. Depends on the different reservoir types, and each one might have different his own water. It's not only at the bottom; it could be in the middle as well. No, the last one is the acoustic.
Our true resistivity of virgin zone.
It normally boosts, it increases. So if you are not aware of this tortuosity, then you might think it's standard 2, and then your resistivity computer saturation might be inaccurate. So that's why I thought in the RG equation A, M, and N also important to understand. Otherwise, assuming at default values can have misleading saturations.
And also, can you tell that you said that in lateral log we usually emit current. Well, we definitely emit current. So how we are going to emit the current in right direction, because current can go anywhere?
Okay, so this is not a azimuthal measurement. This is not a unidirectional measurement. We measure the resistivity. They have a different depth of investigation as the distance wise, but is reading this way or reading that way or reading that way. It's average resistivity all around the borehole.
But actually it's basically reading the resistivity horizontally, as
no, there you have bucking electrodes, basically, which forces the current to focus into the formation. There's a certain devices on the tool body. Okay, so acoustic, we call sonic as well. Acoustic, sonic are just with the frequency differences. So we want to measure formation, compressional and shear velocities. So this is equally used in petrophysics, GNG, and more in seismic. Geophysicists use more also this data a lot. And that's instead of calling transit time, they call velocity, which is inversely proportional. So in rock particle at rest, in compressional their movement, and then in case of shear is different movement. So compressional is particle motion is in the same direction as the wave moves, whereas in the shear case, the particle motion is perpendicular to the wave is moving this way. This motion is perpendicular is the shear wave. So what do we get out of this? That we want to relate these measurements again to certain lithologies, certain porosity, and also the additional benefits like in fractures, formation damage, mobility calculation. Mobility is like a permeability. A rock strength. Rock is very stiff, consolidated, unconsolidated. Its shear wave, compression wave will be different response. And there is a elastic equations, parameters we can compute out of using these compression, shear, density. So these three measurements very important. And any elastic equation you want to geomechanics study, GNG study, you need to have density log, you need to have compression, delta T compression, delta T shear. So acoustic waves are pressure waves that propagate through the rock formation. They are mono or they are dipole, they are different sources. But this is an acoustic source in the middle, and then you have different waves. So this is basically how the waves propagate. Like you throw a pebble into the water and then it radiate different. This is how it goes. So acoustic waves move through the medium in as a wave fronts, and velocity depends on the characteristics and the geometry of the formation. So if you see with this diagram, basically the waves interact with the fluid in the borehole as well, and then generate different waves, head wave, and then interact with the formation, and then based on their motion type and their slowness, how fast and slow comes, we differentiate that is compressional and this is shear. So there are certain waves, body waves at the earth travel at different frequencies. So the frequency is very important in these sonic waves. So along axis we have different frequencies and then wavelength. And then we see that at different frequency, different wavelength. There is a seismic, VSP, borehole seismic, VSP, surface seismic, 2D, 3D, and then sonic logging, different frequency, different wavelength, ultrasonic at different frequency, different wavelength. So this is the tool body, like a pipe, metal rod. It has a device which basically generates sound wave. We call it a transducer or transmitter. Different acoustic, in ultrasonic we call it transducer. In sonic we call it a different frequency, we call transmitter. So basically it just send beeps or sounds to the formation. At different frequencies will be different responses. So this is like a tool in the borehole, has a receiver and transmitter. Transmitter sending the sound wave, a receiver receiving the sound waves. And of course the sound wave leave the borehole, go into the formation, and then come to the detector, receiver. So basically what we're measuring is the time it left the transmitter, reached the receiver. And we know the distance, and that we know the time and we know the distance, we can find out the velocity. Yeah, at the speed, at which speed it traveled. So transmitter fires, and then timing starts, and detect, and then wave reaching the receiver will have those different types reaching to the receivers. So we call these sonic logs in slowness, not in velocity, but slowness, and the term used called delta T. Why delta T? Because the time taken the wave left this transmitter to reach to the receiver, this is the delta difference between 2 points. And when it goes to the formation, certain formation will slow down it, certain formation will not slow down it, and that's a property of that formation and the fluid inside. So that's why this transit time will vary accordingly. So delta T is the time the wavefront took to travel 1 foot. So that's why we present it delta T in microsecond per foot. This is the unit we use. We have a different tool made in different times with the single receiver in the beginning, 2 receiver later on, and then 4 receivers in afterwards. So of course, as the technology evolves, the measurement is basically improves, and the latest tool will have more sensors, more measuring points, more. So it basically we're trying to be more precise and accurate measurement. So when we analyze a wave reaching to the detectors or receivers, they have so they have different frequencies at different wavelength, and based on that we see the early one, the first arrival, we call delta T or delta T compressional. Sometimes we say delta T only, or sometimes we say delta T C. C means compressional. This is the first one. The next one is slower, is shear. We say DTS or DTSM, different mnemonics, different companies use different mnemonics, but DTS may be short. DTC, DTS, And the last one is Stoneleigh. Stoneleigh is the wave move along the borehole, so it's a bit slower. It's influenced by the mud, drilling mud as well. Sometimes what happens that we don't detect the first motion compressional, and sometimes we're not able to see the shear, but Stoneleigh, the mud arrival comes earlier. So this is based on their characteristics to the formation. Yeah. So in sonic tool, we have different tools, of course, basic, simple, and an advanced tool. And we have in this array sonic tool, you see instead of 1 or 2, we have multiple array sonic receivers transmitted at the bottom, and then we reaching the different wavefronts to all those receivers. Some are close to the transmitter, some are away, because as we interested in the deeper information, and also with that combination we want to see how much early arrival to late arrival, time delay. And as you seen those array waveforms examples at the bottom, there's a less because the wave reaches faster earlier, and as it travel to the next receiver, it is basically delays further. So it means that this is a slant line, and first one compression, middle one shear, and the last one Stoneleigh. This is how their order is. Yeah, so I think, yeah. So the first, this sonic tool has to be, as compared to density and neutron, which we noticed that we were pushing it to the borehole wall. But sonic tool, since we want to write read transient time, so we run it from all directions equal. So we run this tool center, in the center. So the tool, we have certain centralizers on the tool body, keeping the tool body in the center. Not in, because if it goes to the borehole, then it will be more borehole mud signal. As you mentioned that the mud effect on the measurement, that also happens. So that's why any log we basically explain or interpret, we always look at the borehole information. We always has caliper data in front of us. We know the bit size, the hole was drilled, and the caliper. If it's the same reading, our reading caliper is more larger, washout. But breakout mean hole is ovalized. So this borehole information is very critical to explain the logs, to understand the logs. So if there is a borehole large, it will affect density, it will affect neutron, it can affect sonic. But pad tool, the tool which need to touch the borehole, more affected by the bad hole. The tool which is not pad tool are least affected by the borehole. So this is just the certain physics based and tool based design. Yeah.
Okay, sir, in deviated and horizontal wells, I think we cannot use the wireline logs. So what kind of logs would we use in those wells?
No, in deviated horizontal we can use the same tools.
Okay.
The conveyance is different. So in a vertical well, due to or in a low deviation, the tool basically go by its gravity. The tool weight pushes the tool to the borehole. If the angle is, keep increasing the angle, the gravity will not work. So it means you need extra force, external force to push tool downhole. So then we may not run through the wireline, we run through the drill pipe, we run through the mud motors, which can push the tool downward. Or we run logging while drilling, which acquire the data while real time because it's attached to the drilling string. So the conveyance could be issue. The tool design, the tool measurement is not sensitive to the borehole deviation. No.
Okay. Thank you, sir.
Yeah. Okay, all right. So as we mentioned earlier that in acoustic sonic measurement, we will interested on getting all these three measurements: compressional, shear, and Stoneleigh. So in a case of hard formation mean consolidated, more solid, more stiff, will have in case of monopole source will give us compression as well as shear. But in case of soft formation Soft formation, we use term for slow formation. Mean its mineralogy is such that sound wave takes longer time to travel. So the delta time will be higher and velocity will be less. So that's we call slow formation. In slow formation, the monopole source mean the source which basically sends the sound waves all around the borehole in all direction. So that monopole source may not be enough in slow formation to receive in particularly shear data. So in that case, in slow formation, when there is no shear reaching to the receivers, we need, instead of monopole, we need dipole source. So dipole source, in contrast to the monopoles which is all directional, dipole source is unidirectional and it pushes the formation in one side. We also called, instead of shear, called flexural wave, because it pushes the body of the formation in that way. So there is certain corrections or adjustment to convert flexural wave into shear wave. So the dipole transmitters are directional and they have a higher output. They basically they are used different frequency, and also there is a frequency band, because when we say fast and slow, it is not a one fixed number. The slow could have wider range. So that's why it means we need to have a dipole source which works as a wider frequency band. So like geophysicists use this term frequency sweep. So they basically send the sound wave with a certain frequency range. We also have a tools based modern tool based frequency which has chirp drive, sending a range of frequency rather than selecting only low or high frequency. We're not limiting it based on the formation characteristics. So in slow formation, you must need dipole source. So it means the tool body has centralizers and then receiver array and transmitter array. Transmitter arrays are monopole and dipole. Monopole good for compressional, monopole must be used because of compression. Dipole additionally to be used for slow formation shear, and only will come from monopole. And different receivers, as you've seen that close to the detector and away, so you can increase your depth of investigation. Because in a large borehole washout, you want to get deep into the formation. So that's why sonic measurements is mostly good even in your large boreholes or slow formations. And that's why sonic log also being acquired from surface to the bottom of the, because you want to use this log for GNG, for seismic calibration as well. So this is how we present the log. You have caliper gamma ray, the compression shear data, and then towards the end this blue and red tracks. Basically we need to have a certain quality control of those final curves. So basically it's how strong it is, the signal, how strong it is, how continuous it is. So that gives us the confidence on the curves. So it means certain quality control is also important when you look at the basic curves. So acoustic log also can be run in case hole. There's certain measurements, log measurement can do in open hole, and only few of that you can run in a case hole. Resistivity mostly doesn't work in case hole. We have very special resistivity, can work in case hole. If an imaging tool does not work in case hole, formation testing also difficult to work in case hole. So the acoustic works in open hole and as well in case hole. In case hole, you need to have, because when you drill the well, you need to pull over the pipe need to be cemented to the formation. So it need to have good cement to work for the acoustic log, because it need to have some bridging between formation and the casing. So the sound wave can travel in a void space. In a liquid, the sound wave will have difficult to travel. Also the case tool also a different wavelength. different frequencies, and we use not only for formation, but also look at the cement evaluation. We also look at the casing integrity, casing condition for the acoustic measurements. They use different transducers. So as I mentioned already, casing condition, cement quality and placement, the acoustic measure is being used, and good cement is needed to support the casing stream, because once you complete the bore or drill, you need to put a casing so you can complete and perforation and produce, and then the fluid should not migrate from different formations behind the pipe, so you need to have good cement. So for the evaluation we use this acoustic measurement, prevent casing corrosion. If you don't have good casing cement isolations, you might have this blowout and fire incident, and it happened worldwide, very disastrous. So this is cementing and casing integrity over the life of the well. This is very critical. The safety, basically precaution for the life of the well. So when we talk about the transducer, basically it's just a device sending the sound wave at a certain frequency, and it's keep rotating, because you need to cover it all 360 degree around the borehole. As you're pulling up, it keep rotating at a certain speed, so you cover all around the borehole. So it emits ultrasonic pulse depending on the acoustic impedance of the mud and the steel pipe. Parts of energy is reflected back to the transducer, and some goes into the casing. Another reflection occurs between casing and cement. So basically you have casing interface to cement, and then cement to formation. You need to know all these interfaces, how bond is cement with casing, and then cement with formation. So based on these acoustic waves, it gives us the information about that. Looking at their times, you can find out the early arrival, how this reflection is stronger, weaker, because if pipe is free, you will have a sound wave coming right away back to the receiver, giving you that pipe is almost free. So all this information is important for your cement evaluation. So it means we basically analyzing the full spectrum of waves. So by these different ecos, we're looking at the casing, and also in the old well, over the production history of the well, you may be different scaling and deposition and different fluid, corrosive fluids. The casing might be some corroded, mean metal loss. So instead of having actual thickness, it's being reduced. So over the life of the cycle, we run this acoustic tool, we can also find the casing conditions. So this is the log display. A cement evaluation log, which is displaying can also be used for casing integrity in an old well, because in new well we know casing is in perfect condition, unless there is some grooving or some wear and tear during bit passing. Otherwise, mostly on the cement. So we look at that certain colors, certain by blue, yellow, we have certain mnemonic sort of convention to that what this color means. Then we need to look at the log header, of course, and it means that this particular log example saying that the cement is in good. So good cement mean when you're going to perforate, you will have isolation between different formation and fluids. If there is a water below, you don't want water to come make a channel behind the pipe to jeopardize your hydrocarbon production. So let's look at the summary. We're towards the end of 11. I think 11:10 there's the next session starting. So maybe we tea break as well. So we given an overview of well logging. It was logging while drilling, it was wirelining, vertical well, horizontal well. We look at briefly at the well operations, rig up running in different, you look at the equipment, that basically cable type, cable structure, different sheaves. And then we look at also initially the basic petrophysics. So basic petrophysics, key thing to remember is Archie equation. There's a when Archie is okay for its clean formation. When there's a shaley formation, clays inside, different workers have different equation in the worldwide. Dual water equation, Simon-Du, Indonesian. So those different equations take care of different type of clays, different type of mineralogies. What best suited to you, that requires some sort of reading the literature as well as getting some expertise. All right, then we also look at this overview of well logging, and then we spent a lot of good time on different measurements. We covered resistivity, we covered nuclear first, then resistivity. Nuclear was gamma ray, density, neutron spectroscopy, for mineralogy, resistivity, induction, lateral log, acoustic, open hole and case hole, compression shear, and then also look at towards the end for the cement and casing evaluation. So, since we have curves waving, so people care what are these squiggly lines. So these squiggly lines have some sense, so certain meaning, and that by visually you can infer their what they shows, and sometime you need log analyst or software to do drive substitution. You do some hand calculation as well. I think you reading some courses in universities as well. You're doing some projects, get some data from different oil and gas companies, work together. I think this is the best way to learn, is that you get some sort of work as a project, get some data from some island. Here the academia and basically industry need to work together. So basically, because they have the data, you might want to learn. So this is how you need some collaboration in between. So wireline offer quick and accurate way to evaluate potential of well, because this multi-million well is being drilled, so done certain measurements towards the end, and then you need to give the answer in terms of whether well has some potential or not, the over completion or not, and your answer is so important because it is providing the way forward. So different companies does a log meeting when the logging is finished, what to do next. And that is so critical that no wonder that company's CEO is also sitting in that meeting, including all the geoscientists. I mean, some companies are asset structure. Asset means you have geologists, petrophysicists, reservoir engineer, pro engineer, geophysicist, and team lead. And team lead is basically looking at all the aspects and then deciding we go this direction. We complete the well, we load the casing, we do cementing, we do perforation, we do this DST testing. And if there's no potential, we just plug and abandon the well. Because any wise decision want to risk you to have investment further, which is maybe not useful. So nuclear tool measurement allow us to infer lithology porosity, and then geophysical properties, particularly resistivity, give you to infer the saturation. Basically electrical properties to fluid type and saturation. This was the sequence. Okay, so I have quick some questions. So just not test how good you are, but just to refresh here and get myself idea that you were listening carefully. So what are the three zones the formation away from the borehole is divided into? So this is a question. Rather than you can raise a hand, I think. And I have to pick only one. The last one on the close to the wall. Last one close to the wall. Since you are too far, I hope you hear as well. So what are the three zones?
So the nearest one is the flushed zone, the
Yes.
second one is transition, and the third one is uninverted.
Okay, very good. Thank you. Right. Yeah, this is what the answer is. So in this equation, what is missing? Raise hands. Up the RT. What is RT? Resistivity. What T stands for? Or true resistivity. We call true resistivity. We call deep resistivity. We call uninverted resistivity. We call formation resistivity. Different names. T is for true. Why do we use ultrasonic logging tools in case door logging? This is a bit tricky, but you need to try. Ultrasonic logging in case door logging. What are the reason of doing this? आप बताइए पहले. नहीं आप पीछे देख रहे हैं आप. हाँ.
Basically, we have to check the cementing and our casing.
Very very accurate. So thanks for being attentive. Normally I've asked this question before and people say only one of that and misses the other one. So it's good you remember, yeah. So casing condition, whether it's new well or old well, mostly this is being used in old well for casing detection because with the time it wear and tear. And cement quality and placement, this is the initial after setting the cement before doing perforation and completion. This is the primary reason to do that. If the formation density increases, what will happen to the gamma rays? Huh? Decrease what? Gamma ray will be decrease. There will be fewer gamma ray to reach through the detector. What is the reason being? Because the formation denser, not allowing to pass and getting them capturing. So you can see that we have 2 gram per cc rock, denser, and then we have certain gamma rays, and there's out of 4, 3 detected. But if the density goes to 3 gram per cc, then is only few gamma ray. So it means the denser the formation, the less counts reaching to the formation. It means it's more denser. But in terms of neutron, it's also it's opposite. The neutron leaving the source too many, but reaching to the detector only few, high porosity. If they reach more, less porosity. Yeah.
The density is variable, so what would be the response of density in case of shale?
Huh?
The density of shale is mostly variable.
Yeah.
So what would be the response of the density log in shale?
Yeah, it's a good question. I mean, as I mentioned quite oftenly in between that, normally we don't use one single log to interpret. We need log in combination. We use integration format we work. So we look at the gamma ray, density, neutron, sonic, and remember spectroscopy, and potassium, thorium, uranium in terms of gamma ray. So different clays have different density, different neutron, different sonic, and different gamma ray even. But different clays will have different potassium. Some clays are potassium rich, some clays are thorium rich. Illite, chlorite, montmineralized, smectite. There are difference in potassium. So maybe better to judge them on with the spectral gamma ray using potassium, thorium. We can make a cross plot, thorium, potassium, and then they will fall at different lines.
Sir, but won't that be the spontaneous gamma ray that tells us about the radioactivity of the formation? Because in density log we have the induced gamma ray in which we transmit and then receive. So in this case, would it be the induced gamma ray or the spontaneous gamma ray log?
No, this is using a nuclear source. The gamma ray is natural, but the density, neutron, spectroscopy, using a source in the tool, they either inducing the gamma rays or inducing the neutron. But so this is the tool nuclear source. That's why they need to be used with caution, and also be kept in mind if they lost in hole, there will be some consequence because there's a nuclear source. They're not a non-nuclear.
Thank you.
The gamma ray is non-nuclear. Yeah, that's a natural, we called natural gamma ray radioactivity sensor. In a slow formation, would you log a monopole or dipole source? So raise hands. Only one? आप बताइए, चलो सॉरी आप बताइए. In a slow formation, दोबारा देख लीजिए, सोच लीजिए. In a slow formation, would you log a monopole? I think R is confusing, but R is
Yeah.
tricky. Monopole or dipole source? दोबारा बताइए.
Monopole means that it is one and giving the rays to all sides.
Yes.
And dipole is towards one side.
That's correct.
Yeah.
तो ये है कि जो स्लो फॉर्मेशन है
Hmm.
उसमें हमें, मैं आपको ये कहता हूँ, मोनोपोल यूज करें या डाइपोल करें या दोनों करें?
दोनों करें.
क्यों?
I think. क्योंकि it is combination, I think, and we will get the whole picture of.
हाँ, मतलब आप थोड़ा सा एक पॉइंट मिस कर रही हैं, जो आप तो ठीक ठीक दे रही हैं. बोथ जो कंप्रेशनल है, जो डेल्टा टी कंप्रेशनल है, जो बेसिक फर्स्ट मेजरमेंट है, अर्ली अराइवल है, जो कि प्रोस्टी आपकी ड्राइव करती है, वो आती सिर्फ मोनोपोल से. फॉर्मेशन स्लो है या फास्ट है,
ठीक है.
वी मस्ट हैव टू हैव मोनोपोल. मोनोपोल शेयर जो है वो फास्ट फॉर्मेशन में मोनोपोल से आ जाएगी और स्लो की सूरत में डाइपोल से आएगी. तो डाइपोल यूज करने की जरूरत है स्लो फॉर्मेशन में शेयर के लिए, लेकिन कंप्रेशनल कैनॉट कम फ्रॉम द डाइपोल सोर्स, इट विल कम ओनली फ्रॉम द मोनोपोल. सो द आंसर इज बोथ. वी वांट मोर. Okay, that's all. Thank you very much. I hope if was too basic for some, apologize. But if some learn, I'm happy. Yeah. So I work in Schlumberger SLB, and you can contact me future for any advice, for any discussion. Which one? In IP, interactive petrophysics. Yeah,
I
there
think,
is. Yeah.
I think it is an SLB.
No, our SLB Schlumberger software for a log interpretation called TechLog.
Okay.
Check
So, what is the basic purpose of that software? Does it tells us the values at different?
No,
depths of
basically
the logs?
you enter all this data we discussed: resistivity, density, neutron, resistivity, sonic, gamma ray, spectroscopy. You basically get all this data, and as the logging is finished, we give the customers a digital format PDF file. We give the digital format LAS file, DLIS file, right away to the from the well site to the customer. Corrections, calibration being done at the well site. So they load this LAS data to the software. If it's the Schlumberger TechLog, if it's other software IP, there's another called Geolog.
Yes.
UEP used Geolog, IP used OGDC, TechLog used by PPL, and some companies use their own software, third party, so many softwares. But so this software uses all this basic measurement, transform into how much, what is the lithology,
Lithology, right?
fractions, and then how much porosity, 5 PU or 15 PU, or then saturation in terms of SW is as low as 5% or as high as 95%. And then of course other logs, imaging, fractures, identification, stratigraphy, sedimentology, the more advanced things also possible. So it means software basically transforming your this raw data into answer products.
Thank you, sir.
So you can take decision accordingly.
Thank you.
Thank you. Yeah.
Sir, a basic question that all of these values from the log tools are measured during the logging in or logging out? Like the tool is running in or running out?
Yeah, good question. So there is certain measurement we can acquire while going down, which does not require the caliper need to open. So certain we call down log. But down log is good in case of that at the bottom we have some tool failure or stuck situation. We have some data assurance. So certain data is possible in down log, but mostly or always we acquire the data uphole. We go to the TD, we tag the TD, and then pull the tool a little bit, relax for it, so it does not have torque in it, stationary, and then start pulling it. So normally our data is recorded every 6 inch. Its tool is continuously moving, but the sampling is most of the time is every 6 inch, 1 feet, two samples. This is how our data is continuously measured. And at the same time, data is sent to the surface, and the downhole processor and surface units processes in between real time, and what you see besides some electronics, some tool functions or checks, you also seeing density, neutron, as is being acquired at the right time at the well site in our offices through the interact link transmitted right away. So basically, because when you in your rig time, you need to do everything fast. Decisions need to be taken very fast. Rig need to wait for you to analyze things. So that's why it's really designed in such a way that everything goes in speed. So you can, a rig operation goes 24 hours. So it's a day or night or a weekend or either holidays. Someone has to looking at the data and making the answer product right away. Yeah. And also not only we as a service company does, but most of the oil companies do their basic interpretation themselves as well. So it means basically you as a log analyst, petrophysicist, have opportunity to work in a service company as well as into oil and gas companies.
Sir, there is another question that we say, like nowadays, softwares are used for measuring, for data interpretation of the logging tools. So I think then there will be no need of the engineers on the site for these logging tools data or interpretation.
No, interpretation is, as I said, the interpretation is done by well site basic, but final answer product in terms of completion and perforation selection, you need to do certain answer product. The raw data need to transfer into that. But the well site engineer logging is now we have called remote operations. Remote operation mean the engineers are sitting in a certain some maybe Middle East office or Europe or North America office, and they're sending some commands through the network connection. And at the well site, we have only a trained operator and technician who basically combines the tool, load the tool inside, and then because of security reasons, some logistic issues, the most experienced engineer cannot be made available to each well site, right? You maybe can send juniors, or maybe cannot travel. So in that dimension, you think we are already working through this.
So it means
remote operations.
It's must to have an engineer on the site, or it's
no,
even if
someone need to combine the tool.
Yes, sir.
Some need to do some basic checks, put the source in and out, do some calibration. Through the running, you need some physical labor there. Whether it's an engineer or a technician or a trained operator, you need that skeleton. But you don't need to send imaging tool specialist, MDT tool specialist to the well site. It can be done through the remote office.
Okay, sir.
No, normally we use a combination. If you look at log interpretation chart book from Schlemacher or some other, there is basically density on one side, neutron on one side, opposite, neutron and density, and then there is certain lithology lines, the points falling. If you do manual things, the points will fall, either sandstone line, limestone line, dolomite line. So density neutron we use as a combination, not a single, yeah, as a combination. We call the cross plot porosity. We are using density neutron together. Yeah. So for example, if density is reading 2.5, neutron reading 15, what will be the porosity? You put this in a cross plot, the point, that's the lithology as porosity. Yeah. Yeah.
Thank you, sir, for such a broader introduction to the wireline logging. Sir, question is, what are the common mistakes, what are the errors that during interpretation we see which lead to like dry wells and like where our interpretation goes sideways.
But
what
Tariq
is the
Asni Sahab, I think dry well does not lead by logging,
Oh,
lead by the geoscientist who
interpretation.
find the location of the well. Interpretation go wrong. Okay, I think you need to, firstly you need to quality control the measurement. You need to be aware of what we measured and given to you is certain checks you need to pass correct. The log field header has certain calibration, all green, no malfunctioning any sensor. Then also you need to check borehole effect,
Right.
that the caliper is in gauge or not in gauge, and if its gauge has different meaning on the log responses and the separations. You see the resistivity separation, we say invasion. No, it could be large hole as well. Large hole will affect the shallow measurements, the conductive and deep to the formation. So the separation does not mean invasion always or permeability always. It could be bad borehole as well, or it could be due to highly conductive mud, shallow measurement are saturating, not reading the formation but reading the saline mud. So it means you need to quality control, understand the borehole, and then make sure the logs have certain corrections applied.
Right.
Environmental correction we call it. So once you have all this information together, then your other error could be that you're not able to define a right mineralogical model. The mineralogy is complex. It means either you don't have the knowledge,
Right.
or you don't have the measurements enough to drive into that complex mineralogy. So if you're doing a simple solution, the simpler solution could be as wrong as it could be accurate, right? So the uncertainty will be there. How much uncertainty?
Depends on quality of data.
You may not be aware it, yeah? So it means you have to follow all three. Mineralogy first, you fix the mineralogy first by your, also check the model logs, cutting description, read the stratigraphy, ask the well-site geologist, did you notice any pyrite, any different mineralogy? Because sometimes we have low resistivity but hydrocarbons.
Right.
Low resistivity may give you high water saturation, but due to some conductive minerals, this is called low resistivity pay, low resistivity hydrocarbon. So with the more complexities, and Alhamdulillah, Pakistan has a lot of complexities and good challenges, because in north we have different type of reservoirs, in middle we have different, in south we have different. We have carbonates here as low as porosity 0, and does not flow if there is no fractures. You drilled Scacer Lockhart and you found it happy, limestone, good clean limestone, thick limestone, but no fractures, nothing. Because there is no matrix porosity, storage capacity. If you go same carbonate in Middle East, 25 pu porosity, and then resistivity solve the head saturation. So here we found the limestone but no porosity. It means basic log will not give you clue where to perforate and complete. You need to look at the image log, fractures presence, image log, acoustic log, and also look at was there any losses during drilling. So it means more and more information you get together, interpret things in integration format. I think we have asked to stop it because next session need to start.
Yeah, sure. Thank you so
very
much, sir.
Yeah. Thank you, sir. Yeah, thanks for coming. Yeah.